In this video, I will examine how to convert a non-terminating recurring decimal to its fraction equivalent. I will be using a bit of basic algebra for this and will use a few examples to bring out the technique. Let us start with a simple example. Say 0.3 recurring. The bar over the 3 here shows that 3 repeats or recurs forever. Let us assume that we have a variable x which equals 0.3 recurring, that is x equals 0.333 and so on. Let us label this equation as 1. Let us multiply both sides of the equation by 10. On the left hand side we have x times 10 which equals 10x, and on the right hand side we have 0.333 and so on times 10. When we multiply any decimal number by 10, the decimal point shifts one place to the right. So we get 3 point, and since we still have 3 repeating forever, we can write 333 and so on after the decimal point. I will label this equation as 2. Let us now subtract equation 1 from equation 2. On the left hand side we have 10x minus x, and on the right hand side we have 3.333 and so on minus 0.333 and so on. 10x minus x gives us 9x, and if we do 3.333 and so on minus 0.333 and so on, the digits after the decimal point are 3 repeating forever in both these numbers, and the sequence of repeating 3's nicely line up one below the other. So after the decimal point we will get 0, and before the decimal point we have 3 minus 0 which gives us 3. So we have 9x equals 3, which means x equals 3 over 9, which simplifies to 1 over 3. But we have said x is 0.3 recurring, which means 1 over 3 is the equivalent fraction representation of 0.3 recurring. Let us now move on to a slightly more complex example, say 0.47 recurring. The bar here shows that the sequence of digits 47 keeps on repeating forever, which means this number equals 0.474747 and so on. This is different from our previous example where we had just one digit recurring. As before, let x equal 0.47 recurring, that is 0.474747 and so on. I will label this equation as 1. In the previous example, I multiplied the initial equation by 10. Let us now see what happens if I do the same here, that is equation 1 times 10. On the left hand side we get 10x, and on the right hand side we will get 4.747474 and so on. If I label this equation as 2 and do 2 minus 1 as before, on the left hand side we will get 9x, and on the right hand side we will have 4.747474 and so on minus 0.474747 and so on. Let us now see what happens when we do 4.74 7474 and so on minus 0.474747 and so on. In our earlier example, the digits after the decimal point nicely lined up and hence we got a 0 after the decimal point. Here the 7s seem to be below the 4s and the 4s below the 7s, and that is not helping us get a 0 after the decimal point. So we need to do something different. Instead of multiplying by 10, I will multiply equation 1 by 100 and see what happens. On the left hand side, we get 100x, and on the right hand side, we get 47.474747 and so on. I label this equation as 2 and do equation 2 minus equation 1. This gives us 100x minus x on the left hand side, and on the right hand side we get 47.474747 and so on minus 0.474747 and so on. So we have 99x on the left hand side, and let us see what happens when we do 47.474747 and so on minus 0.474747 and so on. Now the digits after the decimal point are nicely lined up, and on subtraction we'll end up with zeros after the decimal point, and before the decimal point we have 47 minus 0, which gives us 47, and hence 99x equals 47, and so x equals 47 over 99, which means the equivalent fractional representation of the decimal 0.47 recurring is 47 over 99. It should be noted here that we have two digits in the recurring sequence, and that's the reason we multiply by 100. Now I'll take up the final example. Say we have 0.547 with a bar over 4 and 7, which means that the digit sequence 47 repeats forever, which means that this number is equal to 0.5474747 and so on. As before, I let x equal 0.5474747 and so on. Let us label this equation as 1. Here the sequence of repeating digits doesn't occur immediately after the decimal point, and since we are familiar with cases where the sequence of repeating digits occurs immediately after the decimal point, I'll try to get the right hand side in that form. For that, I will multiply equation 1 by 10. On the left hand side we get 10x, and on the right hand side 10 times 0.5474747 and so on. Multiplication by 10 will make the decimal point shift to the right by one place. This will give us 5.474747 and so on. Now we have a decimal where the sequence of repeating digits occurs immediately after the decimal point. I will label this equation as 2. I will now proceed as in the previous example. That is, I will multiply equation 2 by 100. This gives us 1000x on the left hand side, and on the right hand side we get 547.474747 and so on. Let me label this equation as 3. Equation 3 minus 2 will give us 1000x minus 10x, that is 990x on the left hand side, and on the right hand side we have 547.474747 and so on minus 5.474747 and so on. And since the repeating sequence in both the numbers line up nicely, we are left with 547 minus 5, which gives us 542. 990x equals 542. So x equals 542 over 990. All we need to do now is to simplify the fraction. 2 is a common factor between the numerator and denominator, and dividing the numerator and denominator by 2 gives us 271 over 495, and we are done. So the fraction equivalent in this case is 271 over 495. In this video, I took up a few examples and examined how to convert non-terminating recurring decimals to their fraction equivalent. I hope you found this video useful. If you have any comments or suggestions, please leave them in the comment section. Also, if you feel that someone you know can benefit from this video, please share with them. If you are interested in more such videos, please subscribe to my channel. Thanks for watching.